Hi, this is Roger from Kanka Labs, today with the third and final episode about selecting a better multimeter. Now, first of all, let's start with some additions or corrections to the last episode. Now, first of all, I couldn't make the 1 millisecond peak function in the 121GW EEV block multimeter made working. Now, after consulting the manual, I found out this only works in AC, even not in millivolts AC mode, also not in AC plus DC true RMS mode, so only in simple AC mode, and it gives you the peak voltage of your input signal. So as you can see down on the left, I've now a sine signal with 2.828 volts peak, which is in fact 1 volts RMS with 50 Hertz frequency, and in the normal AC mode we get of course the 1 volts RMS. Now if we switch to RMS peak, we should get 1.414 volts and we get 1.424. I can't decide here if this is due to the function generator, which has a limited accuracy, or due to the reduced resolution or accuracy of the peak function. Now let's do some experiments. This function could be useful if you have a non-sinusoidal signal and you just want to know what peak voltage that has. So let's change this to a square wave. And each time we have to go out of the peak mode, back to AC, and into peak mode again. And of course we get the same result. Let's change to a pulse voltage and see if this also works. That always should give the same result because I don't change the amplitude there. And we get the halfway correct result of 1.43 volts. Now let's see up to which frequency this works. And let's go up to, let's say, 100 Hertz. And there it took a while until it stabilized, so it seems to be scanning for some time and wait until it has found the largest value. Let's change this up to 300 Hertz. And now we're getting a wrong result, so this only works in the lower frequencies. Let's go back to 200 Hertz. And even there, so 100 Hertz seems to be the maximum frequency. So this is basically only useful for, there you can see the sampling again, useful for very slow signals in the range of the line frequency. Now let's do an experiment and see. That was what the X-Tech in comparison did relatively well. There we could measure also DC voltages. If we are just connecting the probes to a battery at the first moment, this is basically an AC voltage, just like a pulse voltage, and let's see if it can capture that. But it doesn't. It shows 4.26 volts. Let's reset it again. So this is basically not useful or of any use for DC voltages. You see, we don't get a good result. So this function has a bit of a limited use. Anyway, a nice feature, but I like the peak capture function of the X-Tech a lot better, which I find much more useful. So the next thing was how to make the display of the burden voltage working, and at the moment we have 27 milliamps from my power supply, and first of all you see in the normal mode burden voltage display off, then you have to press the setup button for a few seconds, take one of the arrows until burden voltage on is displayed, again press the setup button until you get a beep, And now it still doesn't display the burden voltage. You again have to press shortly the setup, and now we get 77 millivolts. Okay, that is how to make the burden voltage working. And if you change anything, I think this goes to the off mode again. Let's see if we get back. Yeah, you see, we only changed the range button and we are again at burden voltage is off. So this is kind of a one-time function that you only take the effort to make it display when you really need it. Okay, anyway, it works, and a rare feature to find in any multimeter. So next is what you might have already spotted is here. What is this millivolt amps or VA and /VA measurement? Well, this is really a very unique function of the 121GW, and we'll explore it next. So the VA measurement function is basically intended to measure power. Well, why is it not called milliwatts or watts? Well, that depends on what kind of voltage you're measuring. If you're measuring DC like we do now, the multimeter can measure simultaneously the voltage and the current in case you have a common ground or a common reference point over your load. And I'll explain in a minute how this is wired to do this. And you can already see here we have 1547 millivolt amps or milliwatts in that case. And the secondary display changes between the display of the voltage, 5.2 volts rounded, and the current, which is 297 milliamps. And you can see this corresponds relatively well with what the lab supply, which is not very well calibrated. It gives basically within 1% the same values. So how do you have to wire the multimeter? First of all, you can see the current comes in, or the power comes in here through the red lead, goes to our load, which is in this case a power resistor or a string of power resistors, all in all 12 volts. And you can see the voltage is tapped off here with the yellow lead to the volts input of the multimeter, and then the current flows through the resistor and is tapped off down here and goes into the amps, or you can also use the milliamps input. So, and then internally the multimeter measures simultaneously or in sequence the voltage over your load at the volt input and the current here on the lower side of the load through the current input. And the prerequisite is, of course, you must have a common reference. You can either use the low side of your load as a common reference point. In theory, you could also use the high point of your load, but you need a common reference. Otherwise, the internal multiplication of the measured voltage and current would give a false result. So this is a really, well, not unique feature, but in multimeters of this price, you rarely do find this. I don't know of any other multimeter in the 200 euros or dollar region which can display the power with a single multimeter. Well, otherwise you need two multimeters and you have to do the math, the multiplication of your measured voltage and current with a calculator or in your head. So this is for DC power, but when it comes to AC power, that's the reason why this is not called milliwatts or watts, but in fact millivolt amps or VA. And we'll make an experiment just in a minute to see how this works with AC voltages. Alright, let's start with a simple signal, a 1 kilohertz sine wave with 20 volts peak. But the function generator has a 50 ohm output impedance, so this is not a low impedance source, and I've connected it to my RLC box at the moment only by whacking in a pure ohmic resistor of, I don't have exactly 50 ohms, but 47 ohm comes next. Now if you load a 50 ohm source with a 50 or 47 ohms load resistor, then the voltage over the load resistor of course halves. So we don't get 20 volts peak or 7 volts RMS here over the resistor. We only get around half of that value. And you can see here we have 3.4 volts rounded, which is quite near to 3.5 volts. And the current is 72.5 milliamps. And if you multiply this, this gives 245 millivolt amps. And in this case, if we have a pure ohmic resistance, then this is in fact again identical to milliwatts. And we can do a little test if it really measures true RMS by changing to a square wave of the same amplitude. Then we should get with the load 5 volts and we get 5.366. That's near enough. And now of course, because the RMS voltage is higher, we get a higher current and a higher power. So until now everything is okay, but as soon as you have any capacitor or inductor in your load, then everything changes, because then you get a phase shift. And I've done a whole video about this topic, if and how you can measure with a multimeter, even if it's true RMS AC plus DC, if you can really measure true RMS power. And we'll change the setup a little bit. And first of all, we'll change to a pure capacitor, where, as you will know, the 47 ohm resistor now is heating a little bit now with 551 milliwatts. So it should be already warm to the touch. But if we replace the resistor with a capacitor or with an inductor, you know that a perfect capacitor or an ideal capacitor will not heat if you connect it to an AC source. So first of all, let's change back to a sine wave, and we'll change to 3.3 microfarad, because at 1 kilohertz this has nearly the same impedance as the 47 ohms of an ohmic resistor. So let me change the setup. And we go to 3.3 microfarad. And now the interesting thing is, it still displays something around 500 milliwatts. We still have 100 milliamps current and 4.7 volts voltage over our capacitor. But as you will know, there's a phase shift of 90 degrees that is produced by the capacitor. And in fact, the capacitor burns absolutely no power. So that is the difference between milliwatts power, which is kind of heat, or not only kind of, which is basically the heat that is produced. And because the capacitor does not produce any heat, it has in fact 100 milliamps flowing through it periodically and around 5 volts RMS, which you can measure over it. But if you multiply the two values, this gives you something around 500, but not milliwatts, millivolt amps or VA, because this is not true power. And if we change to a series connection of a resistor in series with a capacitor, let's take half of the values. We'll take, let me do the connections right. We go to 22 ohms. And 6.8 microfarad. And now we get some value displayed. Once again, nearly 100 milliamps, 2.9, nearly 3 volts, and 270 milli VA. But again, this is not the true power. And if you're not familiar with this topic, I'll give you the link into the video where I explain this in quite detail and make some demonstrations with an oscilloscope, where you can see the phase shift, and where the oscilloscope, in fact, you can use your oscilloscope if you have a modern digital one. You take one channel for the voltage, one for the current measured over a shunt resistor, and then with the math function you can multiply the two curves, and then you will see the effect that you can measure with a modern oscilloscope, in fact, the true power in watts or milliwatts that is consumed by a complex impedance consisting of resistors, capacitors or inductors in parallel, in series, etc. Or as a black box. You can simply deduct from the curves on your oscilloscopes and from the math function what is really inside your black box and what it really burns. But this is a rather complex topic, not for beginners, but you should know about this effect. So anyway, this is a unique functions, and of course there are multimeters on the market which do a true RMS power measurement, but they are nearly an order of magnitude more expensive than the 121GW. One of the better known ones is the Gossen Metrawatt Metrahit Energy. That's how it's pronounced in German, or you will pronounce this as Gossen Metrawatt, which is the company, and the multimeter is called Metrahit Energy. This measures probably the voltage and the current with two separate sampling ADCs, and it multiplies it in software just like your digital oscilloscope does it. But the Metrahit Energy is between 1,000 and 1,500 euros, so it's much more expensive than our little respectable 121GW. So that was it about the unique VA or power measurement function of this multimeter, and now let's go back to some functions that you can also find at other multimeters. So before I forget it, there is another function concerning AC voltage measurement, and that is, you might have spotted this little 1 kilohertz symbol here. That means that you can insert a 1 kilohertz low pass filter before or in front of the ADC, so that you can suppress any EMI noise, etc. that can creep into your test leads, your multimeter, especially if you're working in heavily EMI polluted environments. It's a little misguiding where the symbol is placed, because you might be tempted to press the MEM button, but in fact you have to press the relative button for longer than a second, and then the symbol 1 kilohertz appears, and we're having our 300 millivolts, and we'll rise the frequency in steps of 100 hertz, 200. Oh, there's already a, no, it has gone back to 303 millivolts, 300, 500. There we already can see a drop of, what is it, 3%, 600, and it starts to drop. And at 1 kilohertz we only have around half the level. So it's not a minus 3 dB point, but a minus 6 dB point when the level gets to half. And let's see when we now increase the frequency in steps of 1 kilohertz. At 2 kilohertz it has dropped to 3% of the initial value, so the filter is quite steep. And this is also a nice addition, not often found in multimeters of this price class. Nice feature to have and very useful in EMI polluted environments. So the next special functions of the two more newer multimeters, that is dB measurement, or to be more precise, dBm measurement. So if you're not familiar with dBs and what is dBm, I've made a separate video with a kind of alternative introduction to understanding dBs, which I will link in down below in the video descriptions. Suffice it to say, for now, dB is always a relative measurement of power, and if you have a letter behind the dB, the ratio of the powers that you measure with dB is not an arbitrary value, but for dBm it is defined as 1 milliwatt of power into a 600 ohm load. So you might wonder, well, why 600 ohm load? Well, 600 ohms is the standard impedance used in recording studios and professional audio equipment. And so this dBm function in measuring AC voltages is especially useful if you're doing repair or adjustment work in audio hi-fi stereo equipment. And if you do the math, 0.775 volts or 775 millivolts into a 600 ohm load, let's take out our calculator, 0.775 volts squared divided by 600 ohms gives exactly 1 milliwatt of power. The 0 dBm reference point corresponds to a voltage of 775 millivolts RMS. But there is a catch. With a multimeter, you're measuring, if you're having no load, you're measuring open circuit. And if you would have a true 600 ohm impedance source and now put a 600 ohm load to it, then of course the voltage would only be half the value, because you get a voltage divider between the output impedance of your source and the load impedance. So you should be a little bit careful. You do not measure true power with it when you display dBm. You're in fact measuring only the voltage, and in the microprocessor this is just converted to dB. But anyway, when doing repair or adjustment work, this is absolutely sufficient. Now, how do we display this in the two multimeters? First of all, the 121GW, we go to Setup, and with a short press we get at the moment 0.014 dBm, so that equals of course 0 dBm. And with the X-Tech, which by the way is a rebranded Bryman multimeter, we go to Select, and we get for a short time displayed 600 ohms, and we get exactly 0.00 dBm. So concerning the accuracy, this is, at least from the paper specs, a bit better than the 121GW, but when you're doing audio repair and adjustment work, 0.1 dB is more than sufficient for every kind of adjustment you do. Now we'll change the voltage down by a factor of 10. We're going to 77.5 millivolts. And we get minus 20.05 dBm, and here the same minus 20.16 dBm. So we get 1/10 the voltage, and this is the classical minus 20 dB. And now what comes in really handy is that you can also of course use the relative button. Here it's the delta, and we're now setting our reference point just to the value that we want. Let's try this here. No, this remains at, which is basically correct. If you state dBm, then you should not be able to rel this out, but the voltage is relled out. When you're really doing adjustment work, you always do this to a reference level that is stated in the repair manual or in the technical specs of your audio device. So I would have liked it if the EV block multimeter could also rel out the dB value. Another feature that you have here, you can not only relate the dBm value to 600 ohm load impedance, but you have a whole range of load impedances going from the lowest is I think 4 ohms, then it's 8, 16, and you have all kinds of fixed selectable load values going up to I think 1200 ohms. Yeah, 1000, and the highest is 1200. And so this is a bit more versatile due to the fact that you can rel out, and you don't have to do the math in your head or with your calculator. So anyway, good to have the dBm display function, but it could be a little bit more versatile by being able to rallying it out. The advantage here is, of course, you have with a dual display that you can see the absolute level of your voltage and the dBm at the same times. But when you're doing adjustment work on your audio equipment, you usually are working only with the dB display. Let's see if this also works in the millivolts range. This one here, the X-Tech, does not work in the millivolts range. You can see the dBm symbol is only for the volts range, but at the moment we are probably having an overload. Forgotten to change to AC. Okay, how far goes this up? Alright, this one works also in the millivolts range. First of all, we have to change again with the setup button to no. It does not display dBm in the millivolts range as far as I can see. So it also does dBm only in the AC volts range. So there is still one special function with the X-Tech, which you also rarely find. Perhaps you can read it. %4 to 20 milliamps. Now in industrial applications, when you have external sensors and you have heavy electromagnetic interference and long cables to your sensor, etc., it's much better to use a current-driven connections that transmits your sensor signal or value. And therefore this 20 milliamps current loop was invented. So a zero value corresponds to 4 milliamps, and that way you can detect cable breakage, etc. So 4 milliamps is the lowest value and 20 milliamps is the highest value, which you can see upon 20 milliamps is 100%, 4 milliamps is 0%. And I've connected now this with my precision current source. And if we press, you might have seen we had, let's go back again. We had less than 4 milliamps, 3.246. And then we get, of course, a negative value, 4.7%. So let's dial in exactly 4 milliamps. We should get nearly exactly 0%, yeah, 0.03. And then if we go upward, this current source only goes to 10 milliamps. You can see the percentage level goes up linearly corresponding to the current. For example, now we are at 9.819 milliamps, and that corresponds in the range 4 to 20 milliamps to 36.367% of the maximum sensor value. So also a feature rarely found. To admit, I've never used it because I don't have any sensors with the 20 milliamps current loop. But in industrial and scientific applications, these current loops for sensors are used quite often. So a very special feature and nice to have it just in case. That was it. Everything to say about anything related to volts, amps, watts, VAs, ohms, etc. And now let's try out the other functions that we have, like component testing and what else we can find.